special types of hyperbolic 3 manifolds, namely those with fiber over the circle. These manifolds are constructed by taking a surface across an interval, surface of genus greater or equal to 2, and then you glue the two ends together by a diffeomorphism, and it turns out that sometimes you get a hyperbolic 3 manifold. So you can sort of draw this manifold pictorially as looking something like this. It's got these fibers. It's a fiber bundle over a circle, and it's got some two-dimensional surface as the fiber. And it's quite surprising in some ways that these manifolds ever have hyperbolic structures. It was a theorem of Thurston that whenever this gluing map is pseudo-Anosov, then they do have hyperbolic metrics. Pseudo-Anosov, if we don't know it, is a fairly generic condition. It essentially means that phi doesn't fix this map doesn't fix any curve on the surface, and neither do any of its powers. So this was known in the 70s that these manifolds exist, but we still don't understand what they look like geometrically very well. Then we can ask what kind of minimal surfaces exist in these 3 manifolds. And the first thing you can notice is that there is a minimal surface isotopic to a fiber. So you can assume that one of these surfaces, these fibers, is a minimal surface. That came out of work of a variety of people, Shane Yao, Sachs, and Ullenbeck. Sachs and Ullenbeck. Work I did with Friedman and Scott showed that the surface, the least area surface of this type was embedded, and this particular result also came out of work of Meek, Simon, and Yao, who minimized in an isotopy class. So we knew that one of the fibers is embedded, and the question, which I believe was first asked by Ullenbeck, is can this type of manifold be foliated by minimal fibers? So can you make all the fibers minimal at the same time? Now, this isn't such a ridiculous possibility because there was a theorem of Dennis Sullivan that was proved a little before this. In 1979, it appeared. And he showed that this kind of manifold, let's call this manifold M sub f. F is the fiber here. This has some Riemannian metric. In fact, this is a very special case of what Sullivan proved, in which each leaf is minimal. This is what's called geometrically taut. If there's some Riemannian metric in which every leaf of a foliation is minimal, then we say that the foliation is geometrically taut. Geometrically taut Sullivan showed was equivalent to topologically taught, which means that every leaf intersects a closed curve that's transverse to the leaves. That's certainly true for these guys. If you take a curve like this curve is transverse to every leaf, and so that foliation by the fibers is topologically taught. Sullivan's theorem tells us that it's then got a Riemannian metric in which each of the leaves is minimal. But any closed three manifold which has this topologically taught condition is geometrically taught. So it admits some metric. What's it? MF is, I'm assuming that this map is pseudo-Anosov, so that it admits a hyperbolic metric. But the metric given by Sullivan's theorem may not be hyperbolic. So question is, can this metric be chosen so that it is hyperbolic? And we still don't know whether this is ever possible, but what I'll show today, and I'll state this more precisely later, is that the answer is sometimes no. So some manifolds of this type, in their hyperbolic metrics, do not admit, cannot be foliated by minimal fibers. So in the hyperbolic metric, we are not able to simultaneously make every one of these fibers minimal. So let me start by just giving a quick sketch of the argument. So I want to, everybody see the Wi-Fi? I want to try to explain a basic geometric construction, which is that hyperbolic manifolds look like cusps near a short geodesic. And this particular construction goes back, is actually found in Thurston's notes. It's called it's part of what is now known as Thurston's Dane surgery theorem. But it's been extensively developed since then. So this picture of what manifolds look like near short geodesics is now quite well understood in very broad context. And some of the people who have developed this theory include Kirchhoff, Cooper, Hodgson, Bromberg, Minsky, and so on. And they've used this type of theory to study ends of manifolds. But the particular results I'll talk about have been known for a long time. In fact, I found some old notes of a conversation I had with Thurston at the Durham conference in 1984. It's a little embarrassingly long time ago. So I thought, what would the moral of the story be that this had been left for so long? And then I remember that I once heard from Avi Wigderson that actually all stories have just the same moral, which is don't do it again. So let me draw the picture up over here. We'll use it again. So here might be one of these manifolds that fiber over the circle. It's got these surfaces. And what we'll see is we're going to be able to construct a sequence of such manifolds, each of which fibers over the circles, but their geometry is going to look sort of like this. Maybe this is the first one. This will be the second one. It'll look very similar in the bulk of its of this filling out by surfaces, but there'll be this very long piece here. You should think of this as really long and getting very thin, and right at the end of it you'll see a fairly short geodesic. So this might be M2, and this we can continue getting more and more of these until eventually we'll get something that doesn't fiber over the circle anymore, but it's actually non-compact. It'll look like this. Call that M infinity. And this end of M infinity is called a cusp. And it looks exactly like an ideal cusp if you go far enough out. So an ideal cusp is just the quotient of hyperbolic space by a z plus z action. You take two commuting parabolic elements, and you'll get this manifold that looks like a torus across the reals, and it has these cross sections which look like tori going out to infinity. And if you take this cusp of this non-compact manifold and look at the part of it that looks like a torus across a half-open interval, it's actually exact. There's an exact isometry between this part of an ideal cusp and this cusp in here. So these finite volume manifolds have pieces that look exactly isometric, that are exactly isometric to part of this infinite cusp. And these manifolds M sub I converge to this non-compact manifold in what's called the geometric topology. So let me say a little about that. So in this topology, what we need to know is that essentially this says that if you restrict to compact sets, so for example, we could take a point x1 here, a point x2 here, and a limiting point x here, and what we see is if you have this geometric convergence, then if you take a ball around, if you take the ball of radius r, or the set of points within r, fixed in r, so for any fixed r, these points within r of this sequence of points converges isometrically to the points that are within radius r of this limiting point x. So these neighborhoods of radius r look increasingly like a neighborhood of radius r in this manifold. In particular, if we look out far enough in this cusp, if you look at these regions, well, you won't see such a region here, but if you look far enough out, you'll start to see regions that look increasingly like an interval in a cusp. So we'll be taking advantage of this convergence to cusps to construct these examples. So let me just say a few words about the idea. And this is what makes this whole argument work. Supposing that each of these compact manifolds is foliated by minimal surfaces, well, some of these fibers, some of these minimal fibers must go far out in the cusp, because together they sweep out the whole manifold. So that means that there's minimal fibers that go way out in the cusp. Now, one of the things that comes out of this theory of minimal foliations that was studied by Sullivan is if there is such a metric, in any such metric, if you have a minimal foliation, leaves are not just minimal, they're area minimizing. So leaves minimize area in a very strong sense. Namely, to be area minimizing means that if you take any compact subset of a leaf, in this case they are compact, so if you take any closed subset, any subsurface of a leaf, it's the smallest area surface with the same boundary in its homology class. So you have this, if you have these surfaces going out, which are very strongly minimizing in area, then you get a contradiction as follows. Let's look a little bit at the geometry of a cusp. So we can just work in this ideal cusp, which is gotten by taking hyperbolic 3-space and modding out by 2 parabolics, so we get a torus cross I. In fact, it's convenient to look at this in the universal cover, which I'll take to be the upper half space. And the metric in the upper half space looks like this. So what this means is that distances grow linearly. If you're not familiar with this, one thing you can think about is that these cones, these are the cones of constant distance from the z-axis. So this distance up here is the same as all these horizontal rays have exactly the same distance. So in particular, we can look at the universal cover of this cusp in this model, and we'll see that there are these 2 translations, which are hyperbolic isometries, parabolic hyperbolic isometries, and a fundamental domain for that torus, for one of these tori, let's call this one T sub s. So a fundamental domain for it is one of these horizontal quadrilaterals. And as you go up here, you'll see that actually the area of these tori gets smaller. It's easy to make the calculation of how quickly it grows. It gets smaller. Area drops like the square of the height. So as you move up in this cusp, using z as your coordinate, then area goes down quadratically. So the area of these tori go down quadratically. But what happens if you had some kind of a surface sticking up into the cusp? So let's suppose for now that it intersects, say, well, let's suppose that it had a couple of parallel circles on this torus, and you had an annulus that went way up and down again. What's roughly the area of such an annulus? Well, if you compute what an infinite vertical rectangle contributes to area, you'll see that the area for infinite rectangle is about the length of its boundary curve. It turns out it drops linearly as you go up, not quadratically. So if the area of these surfaces that go way up into the cusp drops linearly, and the area of these tori drop quadratically as you move up, eventually these tori will be smaller than these long surfaces that go far up into the cusp. And then you can save area by taking a shortcut in this torus instead of going all the way up and down the cusp. So that's the idea of the proof, and then it's just a question of making it a little more precise. And in fact, you can prove something much stronger than that there's no minimal fibration. And I'll make a more precise statement shortly. But basically, the idea is just the different area growths of these tori and of surfaces that go up vertically a long way.
What about the case that the intersection is an annulus instead of a disk?
Well, in this case, I was talking about the case where it was an annulus, but it went up a long way, and then the annulus came down. So this was a boundary parallel annulus, actually. But it could, of course, be trivial disks as well. So I'll say something a little bit more precise about the two cases in a minute. So before I get into a little more detail on the proof, let me talk about a little bit more about how you explicitly construct such examples. How do you get these examples where each of these approximating manifolds fibers over the circle, but the limit has a cusp? Yes, question?
The fibration is part of the story or just a manifold? You're allowing yourself to change fibration at the same time.
I see. So you're saying, can this maybe have many different vibrations, and some are minimal and some are not? Yeah, so it turns out that none of them will be minimal if it has more than one vibration. Another question? So let me say a little bit more about constructing these examples. So what you can do is start with any manifold that fibers over the circle. Well, and we'll construct it like this. Well, we'll take it like this. There's a theorem of Penner on how to construct pseudo-Anosov maps. There's actually many constructions that we could have used for pseudo-Anosov maps, but this one is particularly easy, so I'll refer to that one. And it says that if you take a surface of genus bigger or equal to 2, and you take two collections of curves on it, so this might be C1 and C2, and then you have more curves like D1 and D2, and you need more than I've got here. You need them together to fill the surface, which means that they cut it up into disks. So if you have if you have a collection of curves of this type, then if you take phi to be a product of Dane twists along these curves, where you take positive Dane twists for each of the curves in C, and negative Dane twists for each of the curves in D. And you can take any powers that are positive and negative, so I'll just actually take them in any order as well. Then you'll get a map that's pseudo-Anosov. So you'll get a hyperbolic bundle out of such a construction. And now, So we'll call this the manifold that you get out of this M1. Well, we'll call it M sub n. So n is the number of twists that you use along the first curve. So C1 might be this curve over here. So doing a single twist along C1 will already give you a hyperbolic manifold, and so will doing n twists. Well, Mn, and for different values of m, and these manifolds Mn are related. They're clearly all fibered over the circle, and they're all hyperbolic. And in fact, Mn is n minus 1, 1 Dane surgery on M1. So you can add these extra twists around C1 by taking this manifold M1, removing a solid torus around it, and gluing it back after doing the surgery. And Thurston's Dane surgery theorem now applies directly to say that as n goes to infinity, these manifolds converge in this way to a manifold with a cusp. So that's an explicit construction of manifolds having that geometric behavior. Okay, so now let me say a little bit more in more detail about the proof. Maybe I didn't want to erase that. First of all, when we parameterize these tori, call one T sub 1 and T sub s, we have a choice in how we pick this parameter. And what we can do, each of these tori, we fix a cusp now. Each of these tori has a certain area and certain injectivity radius, and this injectivity radius goes down as s increases. In fact, it goes down linearly. So what we can do is require that the injectivity radius of T sub s is equal to 1 over s. Okay, so that's how we'll choose s. That just makes the computations easier. It's the flat metric on the torus, right? So here I'm measuring distances in the tori using the intrinsic metric of the torus. Okay, so let me give a definition now. So we've heard of quasi-geodesics earlier today. We can make a similar definition for minimal surfaces. So we'll say that a C lambda quasi-area minimizing surface F satisfies two conditions. The first one is that the absolute value of the mean curvature of F is smaller than C everywhere. And the second one is that for any compact subsurface, F0, we have that the area of F0 is smaller than lambda times IF0, where this represents the smallest possible surface area of all competitors. What's that? H is the mean curvature. So An area minimizing surface would be one which had mean curvature 0 and lambda equals to 1. That would mean that you couldn't replace any compact subset with a smaller surface. Now, actually, this definition may not be the simplest. You probably small lambda would imply that H was small as well. So, on G, well, I've been vague about that. You could require it to be homologous or homotopic, or whatever class you want to work in. In our case, yeah, it doesn't matter. Say in the same homology class if you want to be explicit. So actually, the theorem that I'm going to prove is that that these manifolds we talked about so let me state the theorem now explicitly. So this bundle with the hyperbolic metric, and by this I mean if you go far enough out in the sequence and choose that n, so for n big, does not admit any foliation. Doesn't have to be a fibration, but a fibration would be one example by surfaces that are one half, 3/2 quasi-area minimizing. So even if you perturb quite a bit, you can't get a fibration by surfaces that are roughly minimal. So there's two simple lemmas that imply this theorem. So let me state them. So lemma 1. So we'll be working in a cusp, hyperbolic 3 space modulo 2 parabolics. And we'll parameterize these tori in the cusps to have this condition. And lemma 1 says that if F is a surface contained in this cusp with boundary on the torus of T sub S, so you have some surface F like this. Is that visible? That blue color? It's okay. So if you have some surface of that type, and the length of the boundary of F is smaller than the injectivity radius, and S is greater than 1, then F is contained in the cusp interval between S and 2S. So you can go out to here, where the torus has injectivity 1 over 2S instead of 1 over S, and this surface will be contained in here. And I'm not assuming this is a minimal surface. This is just an arbitrary surface. Or there's a second possibility that h is greater or equal to 1. So at some point. So if it doesn't, then at some point the mean curvature is greater than 1. I am assuming embedded, but I don't think I need to. They will be embedded in the application. I don't think this needs embedded. I do have to make one more assumption, though, which there's a technical assumption here, which is that pi 1 of f dies in the cusp. Okay, so I'm going to assume that the assumption I made is, in fact, that when you go to the universal cover, this surface lifts to the universal cover. So we have this this lift of this torus at height s is the plane z equals s in hyperbolic 3 space and upper half space model, and the condition that the length of the boundary is smaller than the injectivity radius. The shortest curve on a torus has length twice the injectivity radius. So in particular, this boundary curve has to be trivial. So the boundary curve will lift to some curve on this plane z equals s. And now I'm going to assume that, with the other assumption, we're going to assume that the whole surface lifts. So this surface lifts to some surface in the universal cover. And the assertion is that if it goes too far up, then there has to be a point at which the mean curvature is greater than 1. And the reason, this is a very simple argument, this curve is contained inside a disk of radius I sub s. Yes, I'm assuming that the boundary of f lies in this torus T sub s. But in fact, f can lie anywhere in the cusp. It doesn't matter if you want, you can allow f to go to both sides. But the boundary should be, I've stated it so that f is above s, but that doesn't really matter. You do need to have the boundary in T sub s. And the argument is that that you can draw a disk of radius I sub s on this plane around the curve because it's short enough. And now there's a horosphere which is tangent to the xy plane and contains this circle. And the way I've drawn it, that horosphere maybe looks like this. It's not too high. So that's supposed to be a sphere which is tangent to the xy plane at one point and intersects this plane z equals s in this circle of radius 1 over s. And then the claim is that this whole surface has to be inside this sphere, or there's a point where the mean curvature is greater than 1. And the proof is you just take bigger horospheres otherwise, and eventually you'll get a horosphere that this touches from the inside. But horospheres have mean curvature 1 in hyperbolic space. So at this last point where it touches, you'll see a point on this surface where the mean curvature is bigger than 1, bigger or equal to 1. So that's lemma 1. And a slight generalization of this is lemma 2. Oh, where did the 2s come from? Well, you have to do a calculation. See here, s is Yeah, that's a good question. So S is this distance. So by requiring S bigger than 1, I assure that this intersecting circle lies above the equator. And once you're above the equator, this sphere has height less than 2s. Right? S is the height of this circle. Let me draw it in cross section. Here's S. The height of the sphere is 2s. It's 2. So this height is less than, well, this height is less than 2s, right? This h is less than 2s. So this surface can't stick out of this smaller sphere. If you have S, then it can just reach 2s with mean curvature 1, if it's the equator. So lemma 2. So now I'm going to assume that pi 1 of f is incompressible in the cusp. And we'll take S to be bigger than a constant capital S, which is twice the area of T sub 1 to the 1/3. So this turns out to be how high up in the cusp you have to push things to make them work. So F is going to be a compact surface, and the lemma says one of the following three conditions always holds. Either the mean curvature of F is greater than 1 at some point, and again, this is for an arbitrary surface. We're not assuming F is minimal. Or the area of F is greater than twice the infimum of areas for its boundary. So it's off by a factor of 2 from being an area minimizing surface. Or F misses F lies below the height 4s. So its intersection with the part of the cusp above 4s is empty. So again, this is a result about surfaces in cusps, in the quotient of hyperbolic 3 space by z plus z action. And the argument is very similar to what we did before. So case 1 is that F lifts to H3. This is the case we looked at before in lemma 1. So in lemma 1, we learned that in this case, either F is contained in S2s or H of S is greater than 1. This time, we haven't assumed anything about the length of the boundary of F, though. So we have two cases. So suppose, now that that 1 and 3 fail. So the mean curvature is smaller or equal to 1 everywhere, and the manifold doesn't poke out beyond 4s. But then we want to prove that, that manifold does extend beyond 4s if 3 fails. So if 1 and 3 fails, we have to show that, in that case, 2 must hold, and then we'll be done. And we do that just by computing the area. The area of F by the co-area formula is bigger than the integral from s to 2s. And I'm assuming that s is bigger than this constant of the length of F intersect the torus at height h. And then in the upper half space, let's call this Tz, and then we use the metric in the upper half plane model to compute the formula for the area. So this inequality is known as the co-area formula. It would be equality if this was perpendicular to the Hara tori, to these tori, but it's in general an inequality. You might have more area than you get by integrating this. And then this is the integral of well, let's see. We can assume if this fails, if this pokes all the way out to 4, if F pokes all the way out to 4s, then we can assume that nowhere between s and 2s does this condition hold, right? Because if this condition held for all z between s and 2s, then F couldn't poke out beyond 4s. So for every z between s and 2s, which is where we're integrating, this condition must have failed, which means that this length is bigger than 1 over z.
This was in the compressible case, right?
Yeah, well, in the case where it lifts to h. No, I've assumed that F lifts to h3 for now. And that's the condition that we had here. Case 2 will be where it doesn't lift to h3. So we can do this integral, and I did it ahead of time, and it gives us s, little s actually, so I shouldn't draw it too big. Okay, so this is bigger or equal to s. Now, we know that because this surface is null homologous, it's the boundary of this curve bounds a surface in this cusp, so it's null homologous in this manifold, and that implies it's null homologous on the torus. So it bounds a surface on this torus, which means that the infimum of area of all surfaces that it bounds is smaller or equal to the area of the torus T sub s. Let me write it like this. But now, the way we've chosen S, we've chosen that S is bigger than capital S, which is given here. So that implies that little s cubed is bigger than the cube of this, which is twice the area of T sub 1. Right, so here was T sub s, and this surface had boundary that lay on. This surface has boundary that lies on T sub s. What's that? Why is the surface area minimizing? I didn't say it was. I'm just estimating the area. This is the infimum of all possible.
All right, that's the
All possible area, the areas of all possible surfaces with the same boundaries F. I'm getting more questions than the other speakers. All right. So, right, so S cubed is bigger than this, which is equal to the area of T sub S times S squared. Because remember, as S increases, these areas decrease quadratically. They scale down quadratically. So the area of T sub S times S squared is the area of T sub 1. So S cubed is bigger than this. If we divide by S squared, we'll see S is bigger than twice the area of T sub S. And right, because I sub F is smaller than the area of T sub S. So we've shown that if 1 and 3 fail, then 2 holds. So that, I mean, maybe I made this more complicated than it needs to be, but the idea is very simple. If you have a short curve at some point, then you can't poke up too high without having positive mean curvature. If you don't have a short curve at each point, then you can integrate the lengths and get too much area, more area than there is on a boundary torus. And there's another case, which is where F doesn't lift. So let me just say a bit about that. Well, what you can show in this case, if F intersect TZ contains an essential curve, for each Z in S2S, then well, essential curves are longer than 1 over Z, so this same argument then will apply. And if it only contains inessential curves for each Z in Z2S, then the incompressibility implies that these curves bound disks, and then it does lift to the universal cover. So that's roughly the argument. Now to finish the proof, you just notice that if each one of these is foliated by minimal surfaces, then there's, because of this geometric convergence, there's diffeomorphisms phi I, where phi I maps the cusp from S, 4S on this manifold to the corresponding interval on this cusp, and these converge to an isometry, and this isometry, this diffeomorphism will eventually take an area minimizing surface to one that's epsilon 1 plus epsilon, quasi-area minimizing. Yeah, here?
This one, yeah, the right hand side is that 1 over 2S, is it the S?
Did I get that inside out? All right, well, maybe I blew this calculation, but let's see. This is minus 1 over z. Right, so it's 1 over 2s, right. Yeah, that's right. It's 1 over 2s. And okay, so I got the computation wrong here, but there is a correct, I got this statement wrong. Maybe this needs to be the reciprocal of that or something of that sort. But the ratio of area and length implies that there's some s that will work. I incorrectly computed what the s is over here. Well, shows you should know calculus, I guess. Let me, just in the last 2 minutes, talk about some questions. So one question is, will this work in general? Is it conceivable that this approach will rule out all possible minimal fibrations? And it depends on how accurately you can make these computations out near a cusp. And it's certainly feasible. Some evidence for this is that there is a sweep out by harmonic fibers. So it is possible to take a one-parameter family of fibers, starting and ending with one of these fibers, each of which is parameterized by a harmonic map. Unfortunately, they won't be disjoint and they won't be embedded in general. But these are negatively curved. Let me correct this. These are negatively curved. And in particular, the fact that you can find a family of negatively curved surfaces filling up this manifold implies that there exists some geodesic whose length is bounded. And you can get some bounds. One bound is, for example, if you look at the radius of an embedded disk in the surface, if that's too large, then you'll have more area than you can get in a negatively curved surface. And that shows you, for example, that this R satisfies some inequality like that. So you can get explicit bounds. Actually, this the best possible bound would come from systole estimates on what the size of smallest geodesics can be in a surface. And so, for example, it's known that that such a length is smaller or equal to 2 log. So this is a more sophisticated estimate due to Boozer and Sarnak. And asymptotically, it's known that this is smaller than log of g over square root of pi g. That's a result of cats. So it's not these estimates are fairly robust. So it may be that it's good enough to do the general case. I'm not sure. You know, one thing to keep in mind is that this value s is like the log of the the exponential, the hyperbolic distance is the exponential of s. So this distance from s to 2s is actually, the hyperbolic distance is like the log of s. It's not that big in the hyperbolic metric. This is just a surface. These are results about surfaces. The length of the shortest geodesic in a surface, there's always one geodesic that has length less than this. Now, if you have a negatively curved sweep out, then one of those fibers, well, each of those fibers is negatively curved. So each of them has a curve of length less than any of these three constants.
What are you supposing about the surface because this estimate?
That the curvature is smaller than -1. And that's true for these sweep outs. And as a final remark, that there are other so basically you can think of this obstruction to minimal foliations as being short geodesics, but there's other obstructions. For example, if two of these surfaces have different areas, if two surfaces in one of these bundles have different areas, then it can't be foliated by minimal surfaces. It can't be fibered by minimal fibers. And if there's an unstable minimal surface, then it can't be fibered by minimal fibers. So there are other types of obstructions to finding minimal foliations. So
One unstable minimal surface or one of the fibers?
if there's a, what's that?
There's one
Right.
different unstable minimal surface?
If there's an unstable minimal surface in the homotopy class of the fiber, then you can't fiber by minimal surfaces, as you well know. Okay, I'll stop there. Thanks.